Okay. So a partial derivative is just essentially it's the same process as a derivative, but you have to treat everything constant except for one variable, and then you can take another one with a different variable and everything, and all other variables treat. It's easy to see, but basically that's all we're doing. So in these first few examples, we're just finding df dx and df dy. F is the function itself, and x and y are the variables you take into derivative with respect to. Holding the one in this case, there's two variables. One of them is going to be constant in each case. So 2x squared minus 3y minus 4. If we take the derivative with respect to x, and we hold y, basically we're holding everything else constant. So 2x squared becomes 2 times 2x. That's the derivative of x with respect to x. You know that 2x squared, you take down, it's 2 is a constant, so x squared, and so you take down 2. Minus 3y. So no x value, that means this is like 2 or 1 or 5 or 10. So 2y is basically becomes 0. I mean 3y. 3y becomes 0 because it's constant. And minus 4, that's 0, constant. 2 constants, so it becomes just 4x. 2 times 2x is always MS. And similarly, 2x squared is constant when you take the derivative with respect to y. 3y becomes just, minus 3y becomes just minus 3, and minus 4 becomes 0. So you get 0 minus 3 minus 0 equals negative 3. And number 3 is kind of just like this. So we have x squared minus 1 times y plus 2, like these two binomials. So y plus 2, when you take the derivative df dx, because we had df dx, you can just say y plus 2, that's constant, the expression is constant, so it's multiplied by the derivative of x squared minus 1 with respect to x, so it becomes y plus 2 times 2x. So x squared minus 1 is just 2x, the derivative of x. So it becomes 2x times y plus 2. What was that? Just rearranged it so. And the f dy is x squared minus 1 as a constant times the derivative of y plus 2. Derivative that with respect to y. So it's x squared minus 1 times 1, so x squared minus 1 is your df dy. df dy. df dx is 2x times y plus 2, and df dx, df dy is x squared minus 1, while df dx is 2x times y plus 2. Most of this is going to be following, though. I'm just trying to make sure it's understood at the beginning. But it's more easily explained on paper, most of what's going on. So f of xy equals xy minus 1 squared. We have to do the power rule. So xy minus 1 is dragged out, times 2, drop down to 2, and then it's times the derivative of respect to x, the partial derivative of respect to x, xy minus 1. So this becomes the same times y, so it's 2y times xy minus 1. And the same situation, so df dx is 2y times xy minus 1. Df dy will be the same exact thing, except it's going to be 2x times 2xy minus 1 for a similar reasoning, as you can see. Same type of same power rule used and everything. So now f of xy is equal to natural log of x plus y, so we have to use our derivative of natural log like before, pretty much. So df dx equals the derivative with respect to x of x plus y in the numerator and x plus y in the denominator. So x plus y's derivative will be 1, no matter which way you take it, because x and y are just, the derivative of x with respect to x is 1, the derivative of y with respect to y is 1, and the other variable will be constant anyway, so it'll just be 0. So 1 divided by x plus y and 1 divided by x plus y are two partial derivatives, the first order ones, because we're just looking at the first order ones in these first few examples. Now it's time for one with, we have 3 different partial derivatives for the first order. So we have 1 plus xy squared minus 2z squared. And fx is the Fy and Fz are, of course, other notations. Partial derivatives. So 0 plus y squared times 1, because, you know, derivative with respect to x, it's y squared times 1, and minus 0, so y squared. It's similar as before, it's just having z added into it. Derivative, you know, fy is x times 2y, because with respect to y, x is a constant, like y squared was a constant in fx. Fy, x is a constant, so it's 2 times y. And fz is just the same way. Negative 2z squared is the only thing that matters because these don't have any z values, so they're both constants. And it's negative 2 times 2z, because you drop down, the power comes down. Negative 4z is what you get. Okay, and I would say not to worry too much about these, because these come up sometimes in examples from Calculus 2, typically experienced. Your derivatives of your inverse trig functions. Technically you can think of it like this, where you have du dx and, you know, 1 divided by square root of 1 minus u squared, all those conditions. It's here. Don't worry too much, but you can understand the application is very simple. If you did know the derivative off the top of your head, it would be not too much any more difficult than these other derivatives. I think the natural log and exponential functions are more commonly used in this in any type of normal situation. Okay, now it's time for natural log of x plus 2y plus 3z. Okay, so the denominator is going to be the exact same thing for all three of them, because it's the original function when you take a natural log's derivative, or partial derivative in this case. And yeah, x plus 2y plus 3z is a very simple derivative each time. With respect to x, it's just 1 plus 0 plus 0, 0 plus 2 plus 0 when it's with y, and 0 plus 0 plus 3 when it's with z. And that gives you the slightly different partial derivatives. Okay, in 41 I'm just going to show you all the second order partial derivatives pretty much, as well as the first order, because obviously you have to do the first order to get second order. These are what these last ones are about. It's the second order partial derivatives is what it's mainly about now for the last few examples. So x plus y plus xy, the f dx is equal to 1 plus y, because x is just 1, y is a constant, and xy, y is a constant, so yeah. Then the second order, this type of one, d squared f dx squared, is the derivative with respect to x of 1 plus y, which is equal to 0. The f dy is 1 plus x for similar reasonings, and next one, the second order, just directly from it, is 0. And d squared f dx dy is the partial derivative of x, you know, d dx of 1 plus x, which is df dy. So because you do the first, basically the first, and then you're basically doing it on the second one in the order. The ordering of that is dx dy, so it's dx out front, and this is df dy here. So it's 1, because 1 plus x just be 1. It'd be 0 plus 1, you know. Just show the 1. Same with this one, 1 plus y's derivative with respect to y is going to be just 1. Okay, in this one, x squared y plus cosine y plus y sine x. We have 2xy plus 0 plus y times cosine x equals, the derivative of g with respect to x is, you take down the 2, cosine y is just going to be 0 because y is constant, so anything involved, cosine or sine of y will be 0 because it's just a constant. And y times sine x. Respect to x, it'll be y times cosine x because y is constant, so it's just sine x derivative. So that's how you get it. So 2xy plus y cosine x is your derivative, partial derivative. dg dy is equal to x squared, because y is a constant right there, minus sine y. Cosine y's derivative plus sine x, because y is constant, sine x is constant, times just y, so it's sine x will be left. And I don't know, I think that this gets repetitive, so let's just, as you can tell, it's just same thing. And of course, you can follow that, I assume, so let's go on to a little bit harder one here. Okay, so this one takes a little bit of effort to follow on. The derivative of tangent x is secant squared x. W equals x squared tangent xy. We have to use the product rule because x squared and tangent xy. At least in some of these we have to. So with respect to x, you have 2x, because you take that times the initial, this part, 2x tangent xy plus x squared times y secant squared xy. Yeah, tangent xy is secant squared x. Same thing, you just take you have the derivative of the inside, which xy, just y. That's where you get that from. It's somewhat pretty much the normal product rule, just a little bit more. You have to be used to it at this point. And all of these are pretty much advanced, like similar to Calculus 1 examples, though at the end of the day, like the different types of derivatives. With respect to y, the dw dy, you have x squared times, you can take x squared as a constant and not worry about it, so it's just tangent xy. So it's x squared times x times secant squared xy, so x cubed times secant squared xy. Then the next one was x, so that's, you say 2x tangent xy, you have to do product rule on, and you also have to do it on this. So you have two product rules. So the derivative of 2x is 2, that's times tangent xy. And it works out, you have 2x times y secant squared xy, because that's tangent xy, so it's 2x from the initial part. You multiply by, yeah, so that's normal. Then it's 2xy secant squared xy, because we have to take derivative of this. So we take 2 down, so it's 2xy secant squared xy. Then the final part of the second product rule is x squared y times 2 times y times secant xy tangent xy secant xy. That's because you have to do like the chain rule kind, well, not really chain rule, but whatever you call it. Sort of unofficially, but it's more like the power rule, because secant squared you take down 2, then you do the derivative and you keep the initial, and then you do, you should be able, I think it's explained well enough and ran out, not explain every single little detail in words. But that's kind of what's going on, though, is when you have secant squared, take the derivative of secant squared of x, just x in general, would be, if you just had secant squared x, and take the derivative of respect to x, it would be, in normal calculus, it'd be 2 times secant x times secant x tangent x, because the derivative of secant is secant x, secant tangent, So you have, that's how it works. That's why, in this case, it's secant tangent secant, because the original secant had the 2 drop down from it, and the y comes from that, from xy. And then the derivative of just secant in general is, the tangent secant. But, you can see, I hope I've shown enough of this. Just continues on there. Okay, now it's time for something quicker. We just want to find the mixed partial derivatives, as they call them. And we're kind of just showing that they're equal to each other, the two mixed partial derivatives. So in this case, it's 2 and 3 divided by the same denominator, the first partial derivative, wx and wy, as we've seen before. and wxy, you'll get negative 6 over 2x plus y plus 3y squared, and same thing with this. But I think just seeing it is enough at this point. That's how that one works. And then finally this one, w equals xy squared plus x squared y cubed plus x cubed y force. I think you can understand. But yeah, that's it for this though. In general though, the mixed partial derivative theorem holds out for this kind of course. You don't have to worry about them. Generally speaking, the second order ones of that type when they're mixed are equal to each other in general in this course. In a course like differential equations, you actually might have to look at that one time, and sometimes it doesn't always work out.